first batch. This is a national program. We are starting first time in December, first batch. It's going to happen in M2U University in Karnataka. So I am one of the coordinators of this program, PTTS. You might know MTTS is a very famous program which has been running for the last 18-20 years maybe. And this is the first time we are starting PTTS, Physics Training and Talent Search. So I am going to give full course on quantum physics for BSc students. So that is where I am going to sit down and do again all problems myself. Even though I get an assistance of doing tutorials from PhD students, but I decided to do everything on my own. So maybe with this I will try to again get back to this problem solving business. So the last topic which I thought I should cover is this lab frame and center of mass frame. When we are saying that we have differential cross section in terms of theta, the one similar to what we derived by using Rangel vector in the morning, this theta is, what is this theta? You know, if you have a scattering particle, scattering center here, this is a bigger particle, and then there is a smaller particle which is coming from here and gets scattered like this. And if this is stationary, if this does not move, then this angle is what we call as theta. Correct? But in general, this also moves a little bit. So this moves in this direction and this moves in this direction. So in general, what you have is, this is the relative vector between these two masses. And initially this was the direction of the relative vector. Now this is the direction of relative vector. So this is that angle theta that we actually use in developing theory. It is actually the angle by which the relative vector changes. Because you know, the two-body problem we reduce to one-body problem where the degrees of freedom are written in terms of the relative vector. Correct? So this is that.
Only during the interaction it shifts. Once it goes far away, it goes back.
Yeah, but it goes off like this goes off like this, but this line will remain the same angle. Correct?
But it permanently shifts off.
Correct. Because this also moves, right?
For example, do the codes alpha particles, the nucleus is not going to permanently get shifted off.
It gets recoiled.
Come back again.
Yeah, that is okay. So if there are other interactions, it may come back. If there are other bindings, it may come back. But if you are assuming scattering of two body, both are free particles, then there is a permanent change in the relative velocity, relative vector, and that is the angle that we are talking. So now to understand this, if you imagine you have got a center of mass which is at rest, and then this particle comes in this direction, this particle comes in this direction initially, and then after that this particle goes up in this direction, this particle goes up in this direction. So this angle is theta. So in the center of mass coordinates, the deflection angle corresponds to the angle that this relative velocity suffers in the scatter. So one can say that the sigma of theta that we derive using Rutherford's cross section or whatever formula that we wrote down in the morning is actually pertinent to the angle deflection in the center of mass coordinates. But in the laboratory, when you do an experiment, you will not measure that. You will measure actually the angle. This is the angle that you measure. So if this is going in this direction, This is the angle that you measure. We call it as some small theta. So we should have a way of communicating between center of mass frame and the laboratory frame. Essentially, which means that if you have an expression in terms of center of mass angle, how to write down expression, for example, for the differential cross section, how to write it for the laboratory, or how to convert from one to the other. This question is important because that is what tells us what kind of relation we can derive so that we can transform one frame to the other.
So our choice of the center of mass is probably because it's remaining fixed. No.
Center of mass is fixed, or it moves with uniform velocity. When you see from the laboratory frame, center of mass moves with some velocity. When you see from center of mass frame, it doesn't. That is it. So let us define these quantities. So let us first have lab frame. In the lab frame, let us define R1 and V1 as the position and velocities of particle after collision. This position and velocity of particle after collision. And similarly, in center of mass frame, let's call this as R1 prime and V1 prime. Same in center of mass. And V is the velocity of center of mass in lab. Now with this kind of definitions, we can write down the following diagram. So I can call this as V1 and I can call this as V1 prime and this as V. Now what are the angles? This is the initial relative velocity line, and this angle is given by capital theta, and this angle is given by small theta.
What is the horizontal?
Horizontal is the initial relative velocity. That means when the particle is long distance, that is the initial relative velocity line. So in the laboratory, I will find it like this. In the center of mass, I will find it like this. This V1 prime plus V gives you this one. That is, center of mass moves with some velocity. With respect to center of mass, it moves with some velocity. When you add these two things, you will get what is the velocity of the particle in the lab. Okay, so from this, we can write down the following equations. As far as the vertical component is concerned, both have the same vertical component. Correct? Because the projection is going to be the same. This is parallel to this, so the projection is going to be the same.
Center of mass can move some other direction.
Center of mass.
Why should it go along the initial? It should go somewhere else. No?
Yeah. Well, see, the point is the situation in the lab. What we have is that this is at rest and this is coming in this direction. So center of mass will move in this direction.
The center of mass is slightly off that line.
Off? No, it will always be that line.
But momentum conservation requires to go. No. Center of mass is also. Oh,
The center
so
of
that line is the center of mass.
center of mass. The center of mass velocity in that direction. Now you can write down that vertical component V1 prime sin theta is equal to V1 sin theta. Vertical components are going to be the same. What about horizontal components? V1 prime sin theta plus V is completely horizontal, is equal to V1, this is cos. Okay, cos theta is capital theta, and V is equal to V1 cos theta. Now, you can immediately write down tan theta is equal to V1 prime sin capital theta divided by V1 prime cos capital theta plus V. Or I could have removed this and then write this one as V by V1 prime. Now, center of mass velocity can be written as V is equal to M1 V1 plus M2 V2 divided by M1 plus M2, where this V1, V2 are velocities of this particle before collision. Okay? So, before collision, second particle doesn't have any velocity, so this is 0. So, I will call the initial velocity of the, so let me call it like this, M1 by M1 plus M2 is nothing but mu by M2 into V0. So, what is V0? V0 is velocity of the particle much before scattering. Much before scattering. So if I substitute that one here, then I will have mu by M2 into V0 divided by V1 prime. So I will call this one, so let me call this one as rho. Rho is equal to mu by M2 into V0 divided by V1 prime.
So, how is mu by M2 in
This is 0.
Oh,
Okay, so M1 by M1 plus M2 is mu by M2. Mu is the reduced mass.
you are writing in the lab. No, this is
center of mass velocity. Center of mass velocity will be there only in the lab frame.
What is V1 and V0? What is it?
Yeah, I am calling V1 as V0.
V0.
I can call it.
Maybe the velocity should.
Velocity of the initial particle. Initial
Should
velocity.
the
Yes. Okay, so now we have this. Now, tan theta. Suppose if you have some theta like this, tan theta is given by this divided by this. That means this is sin theta and this is cos theta plus rho. So what will this be equal?
1 plus rho
square root of sin square theta plus 2 cos theta plus rho the square, right? This side.
1 plus.
So this is equal to square root of 1 sin square theta plus cos square theta is 1. So 1 plus is 2 rho cos theta plus rho. So from here I can write down cos theta is equal to cos theta plus rho divided by square root of 1 plus 2 rho cos theta plus rho. This is 1 plus 2 rho cos theta plus rho. So this relation
Angle from the left side.
angle in the left frame and this is the angle in the center.
Yes, the angle in the left.
Now you can immediately write down that if I is the incident flux, incident intensity of the particles, if I is the incident intensity of the particles, then 2 pi I sigma of theta into sin theta d theta. This quantity in the lab frame should be same as the quantity 2 pi I sigma of theta into sin theta d in the center of mass. Because some amount of particles, how you are looking at it is not important. So same number of particles will go over a solid angle of d theta or d omega. So 2 pi sin theta d theta is d omega or 2 pi sin theta d theta is d omega. Which tells you that sigma of theta is equal to sigma of theta into d cos theta by d cos theta. D cos theta by d cos theta. Correct? D cos theta is minus sin theta d theta. This is minus sin theta d theta minus sin cosine. So I have to write it. Now I can write down d cos theta by d cos theta here from this expression. What will that be equal to?
What is sigma of theta? The full expression is the full
Yeah,
term
this
is the number of particles.
This is the differential scattering cross section. Correct?
That is number of particles per time per
See,
unit.
if you have a scatterer like this, and you can ask from this, you have some kind of a solid angle like this, d omega, how many number of particles are entering into this solid angle? So this is proportional to d omega, correct? So you will have the number of particles is equal to sigma of theta into d omega, sigma of theta into d omega. And if you are also, so you can write down this d omega as, if you don't have any phi dependence, you can integrate phi, you will get 2 pi sin theta d theta. And you can also, if you also say that you have some intensity, incident intensity, then this will be the number of particles that come into this detector. And that will be same whether you, so this one, this detector, from the center of mass it has theta, from lab frame it has theta, but detector will receive same number of particles. Correct? So I am keeping a detector.
Same in both planes?
Huh?
Will the intensity be same in both planes?
Yes, this intensity has got nothing to do with this. This is an incident intensity. So how much intensity is coming through this? Okay, so I am keeping a detector here. Someone is looking from center of mass frame, someone is looking from the lab frame. Their angles are different, but this number will be same. So this tells me that this is the relation between sigma of theta and sigma of
The
theta.
number for an ambulance, but d small theta is same as number for the angular spread d capital T.
See, the point is, I am putting a detector here, and my detector has some solid angle, which you describe in center of mass frame with capital theta, in lab frame with small theta. But detector is physical, and there is only one detector.
The time should be distributed.
What?
The time.
See, the expert, physically, it is happening in the same time. I am describing it in two ways, that's all. So my measurement will not give me two results. Correct? The number should be same, number detected should be same. Correct? So, now you can use this expression to do this derivative. Now this derivative is, first I do a derivative of this, which is actually 1 by square root of 1 plus 2 rho cos theta plus rho square, then minus 1 by 2 into 1 by 1 plus 2 rho cos theta plus rho square 3 by 2 into cos theta's derivative is 2 rho, and this rho 2 will cancel, and if I take 1 by 1 plus 2 rho cos theta plus rho square to the power 3 by 2 as a common factor, then here I will have 1 plus 2 rho cos theta plus rho square, sorry, this term will be there, right? Cos theta plus rho into 2 rho, and this 2 will cancel with this 2. So I will have minus rho cos theta minus rho square. So rho square will cancel, and 1 plus rho cos theta. So I will have this relation. This relation, I will have the inverse of this relation, and sigma in the lab frame is equal to sigma in the center of mass frame related by 1 plus 2 rho cos theta plus rho square to the power 3 by 2 divided by 1 plus rho cos. So this expression is what transforms the expression that we had in theta to lambda. And this rho, what we have here, what is this V naught?
Initial speed of center.
Correct.
Center of speed.
Yeah.
Initial speed of the particle.
Initial speed of the particles, and this V prime is V1 prime is the mass of the velocity of the particle with respect to center of mass. And now we know earlier we had shown that R1 prime is equal to mu by m1 into relative velocity r. Correct? We had initially when we did reduce the two body to one body, we have shown this. So then you can write down v1 prime is same as mu by m1 into v, where v is the relative velocity of the system. Now from here we can immediately write down that rho is equal to m1 by m2 V naught by V, where V is the relative velocity. But if you are choosing an elastic collision, the kinetic energy, initial kinetic energy will be same as final kinetic energy, and V and V naught will be same. So for elastic collision, this rho is going to be m1 by m2. So you have this rho here. This equation with rho is equal to m1 by m2 is the equation which will transform between lab frame and the center.
What is the total kinetic energy should not change, sir?
Yeah.
This V naught, system's initial kinetic energy is half m V naught square. Final kinetic energy will be both for both parties.
Yeah, for both parties. But you will see that, see what happens in so we have something like this, right? Initial kinetic energy, initial momentum is m1 v naught, correct?
In the lab frame.
In the lab frame, and this is equal to r. So, okay, let me put it this way. When you have a particle here and then a particle at rest, okay, what is the relative velocity here? It's V naught, right? So this is the relative velocity, initial relative velocity, and then final relative velocity when the particle goes here and this particle comes here, this is going to be V. Okay, so the magnitude of that relative velocity will be same. Because it is getting readjusted, that's all. It is giving a part of that velocity here and a part of that velocity there. So because of that, for an elastic collision, we have rho is equal to m1 by v. Okay, so I thought I will just mention this. Of course, there are certain things which probably we did not do. Even though they are there as part of the syllabus that is given. I think one thing which I missed doing is the time dependence of the Kepler's orbit, where we could have obtained Kepler's third law. So maybe that we can read up. That is the only topic I think which is uncovered. Of course, Rutherford's scattering cross section, we did it in a cheap way. Using the American law, but that is, I think, a cute way also.